Welcome back. We hope you all enjoyed some good conversation and good coffee. My name's Justin Manley. I'm pleased to chair this next set of 4 speakers. We have 2 different themes we're going to bring to you here this morning, building on our excellent opening presentations. The first topic area we'd like to talk about is seeing other worlds. We've already seen glimpses of that, whether that's the other world of under an Antarctic ice sheet or the other world of a robot struggling through the snow. So we're definitely down that path. The first speaker today is Taff Morgan. Taff comes to us from the Department of Physical Sciences at the Open University. And in keeping with really our interesting mix here, Taff's got a very interesting biography. You can read the full details, but some highlights include work on mass spectrometers for space programs, over to air monitoring systems for submarines, right? So we've crossed all of the physical domains and the boundaries there with that technology interest. So today, Taff is going to talk to us about down to Earth, from comets to cancer, and a journey about sniffing out in our solar system. And we've asked each speaker to try to work about 25 minutes of presentation to save some room for Q&A. So, Taff.
Thank you, Justin. This is a privilege, obviously, so I'd like to thank the speakers for the chance to speak at such a prestigious venue. And like David, this is one of my tick boxes on my bucket list. So what I'd like to do today is take you on a journey that took about 20 years to do, 4 billion miles, and it's a journey around our solar system. It's mainly in relation to the Rosetta space mission, the European Space Agency project that dared to chase a comet and eventually land on the comet in November 2014. My role, as you just heard, is developing mass spectrometer systems or gas chromatography mass spectrometer systems to analyze different samples from all around our solar system. So hopefully what I'll give you today is a flavor of what it's like to work on a mission where you wait 10 years for the results, and a rather exciting landing sequence as well, and also then translating that technology to terrestrial challenges. So let's start with comets. Comets are some of the largest and most beautiful things in our solar system, as this picture shows from the Southern Observatory. You can see that tail across the whole of the night sky. But in reality, the comets, or the nucleus of the comet that generates that tail, is actually quite small. It's probably a few kilometers across. And this is the picture taken of the comet that we actually landed on, Churyumov-Gerasimenko, named after the 2 astronomers that found it. Comets are actually big, dirty snowballs. It's where most of the light elements, so hydrogen, carbon, nitrogen, oxygen, are believed to reside in our solar system. We're actually traveling back in time when we go to a comet. So something like 4.5 billion years ago is when this comet was formed. And we're going back to look at potentially whether or not the comet contains abiotic compounds. So are the building blocks of life present on a comet? And actually, one of the big questions we were looking for is, could comets have brought water that generate our oceans today from an early collision early on in our solar system? Just to give you an idea of the scale of Churyumov-Gerasimenko, this is it, superimposed over London. It's an image developed by the European Space Agency. You'll be pleased to know that the Royal Institution is actually under the B of Big Ben, so we're not actually flattened. However, the Houses of Parliament are actually underneath this comet. So whether or not this is actually an image from probably about 5 or 6 years ago, so whether or not they were anticipating Brexit, I don't know, but it gives you an idea of the scale. It's around about 4 kilometers across. Before August 2014, we were actually anticipating the comet being the shape of a potato. As you can now see, it looks more like a rubber duck, with a kind of neck area. Now, we don't really know if that's because there's been a lot of emissions from around that region, and therefore that's what's caused it, or whether or not it could actually be 2 comets that have come together early on in its history. And I'll come back to that a bit later. This is the Rosetta launch event. So we actually launched to chase the comet in 2004, 2nd of March. There's a younger version of me 12 years ago with ginger, not grey hair. Next to me is Sue Horn, who's head of the STFC and UK Space Agency planetary mission programs. And the 2 colleagues on her right-hand side is our colleagues from the Rutherford Appleton Space Laboratory. So the instrument we built that went on the mission is actually built in partnership between the Open University and RAL Space over in Harwell. But in reality, the work started 10 years earlier. This is the proposal from 1994 that actually resulted in us building an instrument to analyze the chemical composition of the comet. If you've been around London recently, I'm sure you've seen all the tourists taking selfies. Well, here's one of the world's most expensive selfies, about 1.4 billion in cost to make it. And this is a picture taken as we approached the comet in October 2014 from about 16 kilometers away. And this is quite an amazing image because it has one of the oldest things in our solar system, along with one of the youngest, of course, the spacecraft. And this is a picture taken from the lander across the Rosetta orbiter solar panels, and the comet in the background. And again, you can see the gas jets coming off the neck of the actual comet. So quite a beautiful and iconic image, I hope, for the future. Now, before we landed on the comet, we had to come to consensus. There were 10 instruments on board the actual lander, another 11 on the orbiter. There was engineering requirements, there were scientific requirements, not all of which kind of came to the same. So we spent a lot of money getting a 3D printed version of the comet, so an accurate model of the comet. Having spent several £100 on that, we decided not to mess it up by marking it with ink. And so my colleague nipped down to Morrison's and we got a £1 dock. And actually we ended up landing in J. So J is on the side of the head of the comet, a place now called Agilkia, after one of the islands in the Nile. But what was amazing was we then took this down as part of an outreach program at the Science Museum, and the dock is now one of the exhibits in the Science Museum. So we've now created a £1 dock into a national treasure, so which I'm sure you can go and see. Can I have the videos, please? So rather than me talking about it, I'll show you a video now of actually the week of landing.
The first ever landing on a comet was filled with suspense, surprises and drama. Almost 7 hours after the Philae lander separated from the Rosetta orbiter, Mission Control finally received the signal it had been waiting for.
So we can't be happier than what we are now. We definitely confirmed that the lander is on the surface.
So we are there, and Philae is talking to us. First things he told us was that the harpoons have been fired, rewound, and the landing gear has been moved inside. So we are sitting on the surface. Philae is talking to us. More data to come and to be analyzed right now.
How audacious, how exciting, how unbelievable to be able to dare to land on a comet.
We are the first to have done that, and that will stay forever.
Hollywood is good, but Rosetta is better.
Then the surprises began. The harpoons had not in fact fired, and the lander had made not 1 or 2, but 3 touchdowns. Several onboard instruments, together with sensors and the landing gear, confirm the location of the first touchdown as planned within Site J, or Agilkia. Without the harpoons to secure it down, Philae then rebounded slowly from the surface at 38 centimetres per second. Over the next 1 hour and 50 minutes, it travelled about 1 kilometre before landing again. It then made a small hop for 7 minutes at around 3 centimetres per second before stopping at its third and final destination in the shadow of a cliff. The CONSERT instrument helped pin down a possible location for the lander, from its first landing area, shown in pink, to its second and third touchdowns in the blue region. The NavCam has now confirmed that what was first thought to be a dust cloud shadow was in fact the Philae lander, together with its shadow. Before the landing, we had a combination of imagination and animation to picture the surface of a comet. This is the real deal, the first image from a comet's surface. And the first panorama too, taken by the Shiva imaging system and including the lander's feet. The 10 instruments on the lander all need power to operate, but the unexpected new landing position receives less sunlight, only 1.5 hours a day compared with 7 from Agilkia. Fortunately, the instruments could perform their science, including drilling, and after nearly 57 hours and a race against time to return the data to Earth, the lander completed its primary science mission. Against all the odds, the landing was a success. Philae is now in hibernation and Rosetta is back in orbit around the comet. The orbiter will continue to study the comet until December 2015, including the comet's closest encounter with the Sun in August. For Mr. Churyumov, it was a chance to thank some of the team who helped the first ever spacecraft land on the comet he co-discovered in 1969.
They made the miracle possible. Glory!
Organic molecules have already been detected at the comet, and thanks to the Rosetta mission, we are one step closer to discovering more about the origins of our planet and the emergence of water and life on Earth.
So that was the probably most exciting, stressful, sleep-deprived week of my life. Ultimately, it was successful, and we got data back, which was fantastic. This is us actually on the Friday night after landing, and as you saw, basically, because we landed in a non-optimal position, we had a lot less power from the sunlight than we predicted. So all the kind of science we'd all prepared for and spent months sending up to the lander had to get ripped up. And my colleagues had less than 1 hour to come up with an alternative sequence. For the first time ever, they wrote it correctly and got it right the first time. And the sequence was sent up and it was actually analysed. The reason we were so worried is that we were probably the last experiment to run on the lander before we were due to shut it down for hibernation. And you can see the red and blue line on the right-hand side dropping down. That's the voltages on the lander battery. If the voltage gets too low, it would basically kill the lander. So we were terrified. Basically, where it starts to drop is where we switched on, because we were quite power hungry, and we were terrified. We were the British people who, British scientists killed Rosetta lander. Thankfully, at around about just before midnight, or just after midnight rather, we actually did finish our sequence. The guys had done the calculations properly, and we managed to switch off, and the lander went to sleep. It then woke up again in June last year, but unfortunately, because of our location underneath this cliff, we never got long enough radio communication to allow us to do any science. And the lander is now officially dead, but the actual orbiter is continuing now until probably September of this year, where it will do a controlled crash landing onto the actual comet. This is the instrument we actually built. We took something the size of a car and shrunk it down to something the size of a shoebox. It's an evolved gas analyzer that takes gas from the Italian drill system through a pipe, which allows us then, goes into a chemistry set. We can then separate the chemical species using gas chromatography and detect it using an ion trap mass spectrometer. The ion trap we built weighs less than 50 grams, but has 54 components. It uses less power than a light bulb, and because we use, instead of traditionally you would use a filament in a mass spectrometer, we now use field emission nanotips, which were specially developed for this project. We were the very first thing that went on the lander, as you can see from the bottom right picture. That's actually the lander itself, the internal structure, and there's Ptolemy on board. And what was interesting was, you can see the little pipe that sticks out the top. That was actually our exhaust pipe that went out to the outside of the lander, but actually ended up being where we got most of our sample from. So we ended up sniffing the comet as opposed to analysing core samples. The last time we touched this instrument was in September 2001. It then woke up in 2010. We analysed an asteroid and actually got an Arthur C. Clarke Award for actually measuring an exosphere around the asteroid before, of course, landing on the comet. So what do we actually do? Well, actually the non-nominal landing give us more science. We could actually look at two geographically distinct locations, as well as look at temporal measurements. We ended up sniffing 9 times, one just after the first bounce. And there's my colleague Andy Morse with the data. On the screen is actually real data that came back 9 minutes after, or 20 minutes after the first bounce. So while everybody else was worried about us going back into space, we didn't care, we already got data. Which after having worked on Beagle 2, the Mars lander, was a great relief. So we also then took some sampling. So we had an oven on board, and we actually managed to sniff some of the atmosphere. So what results did we get? Well, we published the first paper in Science, and that was looking at the dust and the gas thrown off after that first bounce through the exhaust pipe. And basically, the building blocks of life are present on a comet. You have complex organic molecules containing carbon, hydrogen, and oxygen, as well as aromatics. We believe that's down to the kind of photochemistry going on the surface, which generates polymeric compounds. One of the most exciting things we actually found was actually from the final landing site, and that was looking at the carbon monoxide to carbon dioxide ratio. Our ratio was completely different to that was measured on the orbiter craft on an instrument called Rosina. Their ratio of carbon monoxide was much higher, an awful lot higher than ours. And the reason we believe that is different is that they're obviously getting an average of the actual measurements coming off the comet, and we're getting a localized measurement. And potentially what that would mean is that the comet is actually heterogeneous and actually could give credence to the idea that it's actually two different comets that have come together in the past. The debate will go on forever on that, but that's one of the kind of potential scenarios. In terms of technology transfer, we had to wait 10 years for that thing to get to the spacecraft to chase and catch up with the actual comet. So we started looking at how we might use our know-how and our technologies for other applications. The one technology that is directly descended from Ptolemy is a miniature gas control valve that we've developed that allows you to take high-pressure gases and meter it out in very small amounts. It's got a very, very low leak rate as well, which is about 100 times better than the existing solenoid valves that are used on commercial satellites these days. So we are currently in negotiation with a UK satellite manufacturer about that valve being used for satellite propulsion. And we have manufacturing license agreements being signed at this moment. We're also talking to NASA about potentially using it on Resolve, one of the lunar missions, and using it for scientific instruments on the moon. We've also got funding from Innovate UK to work in partnership with a consortium of companies led by Surrey Satellites to look at this valve being used for novel propulsion systems. In particular, the HTP system, which is hydrogen peroxide. And the reason our valve is of interest is because it has no plastics or rubbers in the sealing mechanism, and therefore makes it highly appropriate for highly corrosive gases like this. So we've currently got a 12-month project, and we just finished Q1, and everything's looking pretty rosy currently. In terms of technology transfer, again, we don't only just use what we used on Ptolemy. We also have a portfolio of world-leading instrumentation, including a £3 million mass spectrometer system, which has been used for analyzing dust brought back by NASA missions. We also have a big team of multidisciplinary team. So to build things like Ptolemy, you need chemists, physicists, engineers, CAD designers, thermal engineers, software engineers. So it really is quite a powerful portfolio that you actually put together to do that. And so we've been applying that then to a whole range of different application and different sectors, including healthcare, detection of TB in Africa, drinking water testing, flavors of fragrances, forensic and sports testing, and also submarine air monitoring. But all those are done in partnership with end users. So in terms of healthcare, one of the areas we've applied our kind of high-end mass spectrometer systems in partnership with bioinformatics specialists who can actually take the data, and we're effectively mimicking a dog. Dogs were proven back in 2004 to be able to sniff cancer. Our machine is trying to do the same thing, but instead of looking for specific biomarkers, we're saying what is the pattern that is present, and can we distinguish between those? And actually the main area that we're applying it now is prostate cancer. Prostate cancer, 120,000 men a year get a positive PSA test, which is a blood test in the UK. But 2/3 of those men actually don't have cancer, but they've been told that they may have it and have to go through expensive and very invasive kind of procedures. Potentially this will sniff a urine sample and actually allow us to detect cancer in a non-invasive way. We're about to do some more validation in partnership with Oxford University NHS Trust. But potentially it's a robotic system that allows us to get data on people's health. Probably our biggest impact project so far has been developing the air monitoring system that will go on board all future UK submarines. This is the MOD that says it's a step change and a vital piece of equipment. The former business secretary, Vince Cable, also was delighted with the idea that you could translate space technology to other sectors. This is the team that built the actual system, and in fact, Andrew Morris, who's standing behind my right shoulder in that picture, is now at the National Oceanographic Centre, and he's working on ultra-miniature sensors. So Andrew was one of my better people, but we were sad to lose him, but I'm sure he'll do great things for oceanography. There's our system in the bottom picture. It's a third of the size of the current American system. It's faster, it's better, it's cheaper. It does more gases more accurately, has a better user interface, as we heard from the first talk, very important. And basically, for the first time in 30 years, gives the UK a capability in submarine air monitoring. This is I like to show this one because it's a slide from a local newspaper, and it's the first time I've ever been called a boffin. So I can now retire, mine as a scientist, I've made it. So we are working in collaboration with Geraint, the world's largest fragrance company, to develop a robotic system for the first time that gives them quantitative measurements of their perfumes. In fact, this potentially will replace humans. So currently, most perfumes are actually usually evaluated using a panel of people. For the first time, they can actually use a machine to do that. And we're currently about to finish phase C to provide them with an integrated system, and our system's already been used in Paris to actually develop perfume systems. We also, at the Open University, have a partnerships with a number of multinational companies, including some big American companies, and what they're interested in is our ability to be able to take technology forward from concept through to TRL6, TRL7, and of course, in partnership with them, they can take it through to market. We're also working with the Open University on allowing our students, undergraduate students, access to laboratory equipment directly, so they can actually remotely run some of our kit, or in the future we'll be able to run some of our kit and actually simulate some of the research that we're doing with the cutting-edge technology. In terms of commercialization, I've been very fortunate to have two companies go through the European Space Agency Business Incubation Centre at Harwell. So the European Space Agency is very keen on promoting how we can take our technology and translate it. And yes, I am going to smell bed bugs in hotels. So any of those of you in London who get itchy, you might want to lift your mattress up and have a look to see what's causing that problem. It's an increasingly big problem, especially with high throughput areas like London or airport hotels. And basically, we're mimicking Jason. Jason's the guy on the right-hand side, and he's the guy who's a pest controller, but he says he can sniff bedbugs. And in fact, he's right. And if you could look at the literature, bedbugs give off chemicals, and you can actually use those chemical signatures as a way of actually identifying them. The second company is also come out through Harwell, and that's developing a breath analysis system to detect the bacteria that cause stomach ulcers. And particularly, we're looking at the developing world there and producing an affordable system that's based on an STFC-owned patent. I'm only one, I've got two. There's over 300 companies now in the ESA-BIC. And in fact, Matt Edwards is here from STFC. And if you want to have an opportunity to look at what technologies there may be within the European Space Agency across, I think, 20 or 21 different centres across the whole of Europe, then I'd certainly suggest you speak to Matt, and because there's some incredible stuff that's going out there, including uses of satellites and the Satellite Application Catapult, which is also in Harwell. Okay, I'd like to finish just by reminding you that when you build things to go into space, you have to kind of push the boundaries of science and engineering. You have to make things light, small, low power, but they also have to be robust and shock and vibration proof. They have to survive extreme temperatures and environments, and also be able to work autonomously. To do that, you need to have a multidisciplinary team and a multi-center approach. So it's all about partnerships, working with end users and subcontractors. So hopefully what I've done is illustrate that we've developed some new solutions, some new technologies, which potentially provide new opportunities. One of my colleagues actually has an instrument on ExoMars, which hopefully launched at 9:30 today. So in a couple of years' time, we hopefully will have an instrument on Mars. But we're always looking for new opportunities. So if there are any opportunities in the oceanic field, then please join us on our journey sniffing the solar system. Thank you.
Thanks, Taff. I think we're doing okay on time, so certainly struck by the way we look at technology through our own minds, or in this case, we think of it through our noses, right? I'm sure there's some questions in the audience. Anyone have anything you'd like to ask at this time? And we have microphones. Anyone? It's a bright light, so if I'm missing you. Chris, please.
Thank you. Chris Sholin from the Monterey Bay Aquarium Research Institute. Fascinating presentation. Do you have any experience in fielding these instruments below the ocean surface?
Apart from the submarine's obviously been on a 5-month trial, but that's it really. So no, we haven't, but we'd more than happy to look at opportunities.
Questions? Okay, well then I think we'll take advantage of that and stay on schedule. Thank you, Taff. So we're continuing our theme here of looking at other worlds. And again, we have asteroids to icebergs, lots of interesting places. Our next speaker is Dr. Stephen Rock, who comes to us from Stanford. And much like we saw Taff, aerospace and astrophysics into the ocean, Dr. Rock has appointments both in aeroastro at Stanford, and he works at the Monterey Bay Aquarium Research Institute. So he crosses these boundaries. And he's going to tell us about navigating in these remote and extreme environments. So, Stephen.
Thank you all for that introduction. First couple of talks this morning focused on a very broad view of robotics and autonomy in the deep ocean. I'm going to narrow in and talk about one specific technology based on, some emerging technologies that will enable autonomous vehicles to do precise return-to-site visits to spots in the deep ocean. Now, it sounds like, you might be thinking we can already do this, and in fact, we do these missions, but typically these missions to return to a site to sample or to image that site is typically supported by some sort of a surface vessel or surface expression, providing some sort of a navigational infrastructure in order to do that. What we'd like to be able to do is return to sites that, excuse me, I went too fast. I would like to be able to take a map of an area, indicated by the end of that red arrow, put a spot on a map of a terrain and have an autonomous vehicle return precisely to that spot. And I want to be able to do this in environments where there is no infrastructure. This is GPS denied. There are no beacons. The only thing that I'm going to assume that I have is some sort of a self-consistent map. Now, this has obvious applications in underwater research, which is the primary focus of our work here, but it also extends to all GPS-denied environments, or to many GPS-denied environments, in particular, what Taff was talking about in the study of asteroids and comets, but also to studying the submerged surfaces of icebergs. These are all areas of tremendous scientific interest. They are all areas that require, or at least would benefit greatly from having an autonomous vehicle visit the site for safety or just simply access. And they're all sites that have no infrastructure in terms of, they're all GPS-denied environments. Why would we do this underwater? I have a couple of quick examples, but first, let's just say climate change. If you're going to monitor the site, or in order to determine the effects of climate change, you need to be able to go back to specific sites and assess the biology, chemistry, geology of that site over time in order to observe the effects. So there's one motivating mission. Other motivating missions include just understanding the local biology, geology, or chemistry of the site. I picked out two examples from work that have been done at Minbari. The first was work done by Bob Reinhoek a few years ago, where he visited a whale fall, a nutrient-rich site on the seafloor, visited that site for change over about a 3-year period, and as a result of that, actually discovered a new species of worm that's specifically associated with the whale fall. Charlie Paul is a geologist. He's visited a site repeatedly at the 2,900-meter location in Monterey Bay Canyon. These are chemosynthetic clams. Visiting the site helps you understand the biology associated with the chemosynthetic clams. These are clams that live on methane coming up through the subsurface. But they also, Charlie is a geologist, and Charlie is looking at these clams as a biomarker for what's happening to the undersea geology, undersurface geology, in terms of if the clams are healthy, That means methane seeping up through the seafloor. The clams have died. That means the methane's moved somewhere else, and that's the type of a thing that the geologist is interested in. So a couple of quick examples of why you might do it in the deep ocean. Doing it in space. The lower right is the Jupiter moon Europa. There's an ice surface and there's an ocean underneath that ice surface, and this is one of the sites that people are looking to go to explore in the search for life in deep space. I'm not going to try to compete with Taff's description of what happens around comets and asteroids, but let's just say there are other bodies that we would like to explore in space as well. And being able to navigate return to site, perform return to site missions in these environments would be of tremendous benefit. Why icebergs? Icebergs have been shown to be a very nutrient-rich source a source of rich nutrients for a local ecosystem. Recent work has indicated that up to 1/5 of the total carbon transport in the southern oceans is associated with the presence of large icebergs. The icebergs are present, the meltwater gets into the local surrounding seawater, providing iron, other nutrients. This in turn feeds the biology or a food web, which in turn supports the carbon transport. So these things are significant. And again, it's very, very difficult to try to get a ship up close to take dense, repeated measurements against the surface of an iceberg. This is something that you want to do with an autonomous underwater vehicle. One of the things that makes exploration of icebergs and things like comets and asteroids of interest is that when you're taking data and trying to log data in the reference frames of these bodies, these are non-inertial reference frames. So we're not talking about putting our data in an inertial reference frame. We're talking about putting our data in the reference frame of that target body. Icebergs, asteroids, comets translate, rotate. Your compass is essentially of no value when you're trying to do your navigation in that kind of an environment. You have to come up with some means of extending this. This is work that's being done now at Minbari. We're also getting some money from the NASA astrobiology group looking to develop a technology that might actually have some application outside the ocean. So why can't we do it with autonomous underwater vehicles that we have today? Vehicles that are out there, advertise or have inertial navigation systems that are unbelievably accurate now. 0.01 to 0.05% of distance traveled is a specification that's typically associated with some of the more expensive inertial measurement units. This is better than a meter accuracy over a kilometer of travel. Furthermore, when the AUV is on the surface of the ocean, we have GPS. So we know where the vehicle is when we have a location on the surface. If we get down to the seafloor, we can navigate precisely on the seafloor with these accuracies that are reported here. So why isn't that good enough? Well, there are three basic reasons why this isn't good enough. The first is, I might know where the vehicle is on the surface, but if I'm in deep water and I have to go from the surface down to the seafloor, I have lost my navigational precision. I'm flying on free inertials as I move from the surface down to the seafloor. So by the time I get to the seafloor, I may have hundreds of meters of error in terms of locating my position. Again, if I have a surface expression, a ship, I can broadcast with something like a USBL, a location update, and try to correct for that in terms of a latitude and longitude. But if we want to make these missions truly autonomous, I do not have that capability. The second reason is that you don't always have very precise inertial instrumentation on board these autonomous underwater vehicles. This is a quick summary of some runs we did back in 2010 of one of Minbari's vehicles that did not have one of the high-grade inertial systems on board. We were trying to drive from a starting location to a Homer location. This was a distance of about 1 kilometer, and you can see that if we flew on straight inertials, we were off by 100 or more meters in terms of trying to get from our starting point to our closing point. So without the high-quality inertials that give you precision navigation with respect to the seafloor, you also have a problem. The last problem is, even if I do have very high quality inertials. And even if I can locate my AUV precisely with respect to the seafloor in terms of a latitude and longitude, the maps that we're working with are typically not geo-referenced perfectly. Errors on the order of a few meters up to hundreds of meters are common. So the way this, or the reason this happens, is what's shown here in this diagram is a ground track of an autonomous underwater vehicle as it flew over the seafloor collecting sonar imagery that was later fused into a map. In the upper, my right-hand corner, the red circle, this is where the vehicle was put in the water. There was a very precise position estimate from GPS, and at that location we also had bottom lock in our with our inertial measurement unit, so we knew where we were, and we could fly a very precise ground track, but not a very accurate ground track, in that as you flew, the map could either expand or contract, and you have no information to knock that error source out. So unless you have repeated locations within this mapping exercise to geo-reference your vehicle's location, you can end up with a map that, again, is very precise down to a meter level or better, but it's not accurate because it can be warped, it can be rotated, and so you're about maybe 100 meters off or more when you're trying to go to a specific latitude and longitude. So being able to do that's not accurate enough for the type of surveys. We want to go to a specific site, a specific clam field, a specific boulder, and monitor that site for change over time. So, whoops. A technology that will actually enable this type of activity is something, or this capability is something referred to as terrain relative navigation. This is a technology that dates back to the cruise missiles in the 1960s. When you flew in from the ocean on pure inertials, by the time you got to the shore, you were lost. You could have a very large error in your position estimate. So what they did is they flew over a section of terrain that had been pre-mapped. And then they would collect an altitude survey or a profile of the terrain they had just flown over, correlate that against the map, and figure out where they actually were, use that to knock out the drift and the inertials. I'm showing that here. So what's shown here is, this is an AUV, and I'm showing it with a multi-beam sonar. So imagine at a given location, I shoot down with a multi-beam sonar, collect a survey, or a profile with this sonar. I then take that profile that was measured with that sonar, and I slide it along a terrain. This is my map, and there'll be one spot in that terrain where it lines up well, and I'm plotting what's called a likelihood surface or a likelihood score. And what you'd like to think is where this peaks would be a representation of where you actually were with respect to your terrain. And in an ideal world, that actually is true, but in a natural world, what happens is that instead of working with what we're showing down here with the unimodal Gaussian distribution where your true position will likely, I shouldn't use that word, the true position will correspond to the maximum in the likelihood surface. When you're working with true natural terrain, your surfaces, the likelihood surfaces are typically multimodal and very non-Gaussian, so your true location can be quite far off from your best estimate or your maximum likelihood estimate. So the way you get around this is with something called an estimator, or we're using non-parametric filtering. This is something that's emerging that's making all of this possible, that you process this information over time. These measurements of profile can be collected with a multi-beam, a single altimeter, or what we've been working with are the 4 beams that are associated with the DVL, Doppler velocimetry log. We are not the only people to be working on this technology. There are people around the world that have been trying to make this technology work. The 2 groups out there that are doing work that's probably the most similar to our own are the Norwegians and the Swedes. Their motivating mission is a little bit different than ours. We're looking at return to site. These missions are more using this as a replacement for, or their missions are more as a replacement for surface aiding with a GPS fix. To get an idea of how this works, for those of you that might be familiar with Kalman filters and other types of estimators, this is a numerical version of that. It's a Monte Carlo version of that. So what you start with is a series, you basically propagate many, many different hypotheses. We have about 10,000 particles running, 10,000 hypotheses running. So when you start, you populate an area with these different hypotheses. Each one of these hypotheses is a position estimate of X, Y, northings, eastings, depth, vehicle attitude. We're only showing the northings and eastings here, but you generate a broader range of initial hypotheses. As time marches on, each one of these little particles is moving forward, and you can measure that with the inertial measurement unit. At each time, you take a sample, a measurement of the terrain underneath you, and you ask how well is that hypothesis reinforced by the measurements that's being made. Over time, the particles that are close to the true location are reinforced. Particles that are far from the true location are eventually rejected, so we go through what's called a resampling step. You resample once, twice, and as you keep moving along, you eventually end up with a very tight group of particles bunched around the true location of the vehicle. I'm pushing the button. There we go. You can see that happening here. This is a very quick picture. These are northings, eastings, and headings. But the interesting thing here on this plot is watching how the hypotheses are reinforced or are selected over time. We're starting with in northings and eastings about a plus or minus 100 meter positioning error. You can see with the first resample, you threw out many of your particles. These particles are represented by that band of pink. And over time, you keep resampling until after you've flown maybe a couple hundred meters, 100 to a couple hundred meters with the DVL, just the 4 beams on the DVL, you actually have converged on the true location. The way we actually implement it is, I won't go into the details up here, but this is your inertial unit that we would typically be propagating. The inertial unit is offset from a map. So what we're really learning is what is the error in the map's offset. We actually have an update once every 3 seconds, but we're populating this particle cloud. We're going through our correlation. We're coming up with an estimate of where we are with respect to the map. In other words, we're correcting for the georeferencing error, feeding that back into our normal navigation scheme, and then we can continue on our path. I push the button again. How well does this work? Typically, we are working with maps now of the seafloor that are accurate to about 1 meter. And with 1 meter accuracy, I can return to sites within about 2 meters. So if you give me a map that's accurate to 100 meters or a map that's accurate to 10 meters, I can get back to sites within about 20 meters with this technology. These are maps that are typically made with Minbari's mapping AUV over the Monterey Bay Canyon, and I've already shown you that plot up there. Typical example of how this works, these are some results from a study we did at a site called the Portuguese Ledge in Monterey Bay. In that survey, we asked the vehicle to fly a little crossing pattern. We had a target boulder right there that we wanted to go over. This plot here shows 4 runs over that site survey. The important thing on this chart are the color schemes. When the trajectory, we're showing 4 trajectories here. When the trajectory is red, that means the filter has not yet converged. It does not have enough information to determine its location. When it's green, it means it's happy and healthy and is returning a good answer. When the filter is yellow, that means that it is not certain about whether or not to accept that update from the estimator. This can happen when you're flying over relative benign terrain like the flat seafloor. This is typically where we have the yellow plots. Zooming in on one particular run over the seafloor, we asked the vehicle, before we went out, we drew a black line on a map to go over our target boulder. This map actually has about a 20-meter offset georeferencing error, even though it's in shallow water. So if you actually look at the true path that you would fly, that would be this dashed line. So this is, if I georeference or if I correct for the map offset, my solid line would become the dashed line and we would miss flying over this boulder. If you watch what happens with the filter, it starts on the left, it comes in. This is where the AUV thinks it is. The filter has not yet converged, so it thinks it's flying along the correct line. After it's flown over a very small amount of terrain, it actually converges, realizes that it's at a 20-meter offset. We jump up here, and knowing where we are, we then can actually have the control system drive the vehicle back to the true tracking line and goes directly over the boulder. All right. That was underwater. We're actually getting this to work quite well on the seafloor. We're starting to use this in operational missions now. What happens when we try to go to icebergs, or we can dream about going to things like comets and asteroids? This is an animation to define what's happening, or what we have here. This is an iceberg. The 4 little green dots are the DVL footprints. The vertical stripe is a side-looking Rezon, or it's a side-looking multi-beam sonar that we're using for mapping. The little yellow vehicle is, of course, our AUV. And the goal of this animation is to show you what the challenge is when you're working with something that's translating and rotating. Let's see, where do I point this? So what happens is you see the blue spots are the particles or the measurements that you've made with your multi-beam sonar. This is the point cloud that you fuse into a map. We're actually working with an octree representation of the map, but that's not the important thing for here. But you can, whoops, whoop. Okay. The vehicle actually runs pretty smoothly, but never mind. What you end up with is a point cloud. So the pink line there is the trace of the vehicle's location. The point cloud are the sonar measurements that you've taken throughout that run, and you can see that you have this distribution that is not adequate for building a map, so that you actually have what amounts to a true SLAM exercise that you have to go through to cause that point cloud to converge. So what we do is we actually have it's a two-step process. Think about taking as you've gone around an iceberg, think about taking a toy train track, and you get to the end of the train track and you've got these two ends that don't match, so you pull them and you make them match, and then you distribute the error back through your track. So the first step is on the left. This is called a loop closure, or a localization, or a correlation step, a loop closure. So you identify the two sections of your terrain that would overlap, and then we actually are using a graph slam technique, which, just think about this as a nonlinear least squares solver that will take your measurements of the vehicle's trajectory in the iceberg frame of reference as you drove around the iceberg and reconstruct the best fit for where you think your vehicle was. And with that, I won't talk about graph slam. Does this work? In 2008, we ran a preliminary version of this around some icebergs in the Southern Ocean. This is an iceberg it's about 2.5 kilometers in circumference. We put a sonar over the side of the Nathaniel B. Palmer, drove around the vehicle, or drove around the iceberg. Okay. And what you can see on my left is the point cloud of sonar data that we collected before any correction. And you can see the iceberg has actually moved about 200 meters in the time it took us to drive the ship around the iceberg. And then the right is what the point cloud looks like after you've been able to converge. So with this information, we should be able to build a map of the iceberg and then do our return to site visits on the iceberg with the terrain relative navigation. Where are we in the process? We're actually funded by NASA under the NASA ASTEP, the Astrobiology Science and Technology Exploration Program, to build a vehicle. We're doing this with Minbari. This vehicle has several science centers on board, but for the engineering side of it, the vehicle is equipped with a rotatable section containing both obstacle avoidance sonars and mapping sonars and cameras. The red shows this is with the center section rotated so that it's in the downward pointing direction. So we're flying over a sea bottom here where the red is a forward look obstacle avoidance sonar, and then we have a down look sonar. You can see the spots illuminated for the cameras. Not shown in the figure, perpendicular to this, running across the plane right there, is our swath of the mapping sonar. We're in the process of testing this now in the Monterey Bay. We're actually being funded to go up and drive this vehicle around some icebergs north of Newfoundland in June. So this conference happened just a little bit too soon for me. If it had been a couple of months later, we could have shown you some results from this. But to get ready, we've been running down canyon walls in the Monterey Bay, using them as surrogate icebergs to show that the technique works. Very quickly, one of the canyon walls is shown here, where we've come in, done a couple of racetrack loops around the seafloor, collecting our data. This is just projecting the sonar data that we get from a typical run. In order to test the processing we have for doing this on the non-inertial reference frame, or the translating and rotating iceberg, we corrupted the vehicle's compass. We added a bias to the compass, so these are the data as viewed from this fictitious run. And the question is, can we converge back to what we would get around an iceberg? And indeed we can. So these green lines show these loop closure events that we've had as we've gone around. So again, we're just a few months too early, but this is a technology that's applicable to a broad range of GPS-denied environments, and the one we're particularly interested in right now is around icebergs, and I hope to have some data from those runs very soon. Thank you.
So we continue to be doing very well in time. You're not allowed to ask, are we there yet? Obviously, we know that's hard if you're an underwater robot, but other questions are welcome, please. Go up there.
Do you think that the ability to repeat survey to that accuracy will allow AUVs to be used to generate hydrographic quality standard bathymetry charts?
I want to be careful about the answer on that. Repeating the surveys, there are two steps in this process, the mapping step and then the localization step. The mapping step for the underwater environment, I'm not talking about making any changes to how we do the map. So once I have the map, the presentation's been about is using that map for the localization in terms of spots. So I would say that what I'm talking about here probably is not particularly applicable to the mapping side of it, unless you're talking about mapping something that's translating and rotating. And I don't think we're talking about going just there.
Other questions? Okay, well, very good. Thank you, Stephen.